Okay, so as some of the early codecs we were talking about, so I wanted to give you some idea about Reed-Solomon code, which is very popular in storage anyway. And for that, I think in the last lecture we looked at uh, some basics about finite field. I mean, kind of recall what is order, what is primitive element, primitive polynomial, and so on. So the question is now how we can use this information for the construction of Reed-Solomon code. But as I mentioned, so I told you about the cyclotomic coset business as well, right? Last time, fine. So in this original paper, as I mentioned, they used some sort of polynomials. So if there is a message bits, if there are k message bits m0, m1, m2, mk minus 1, you form a polynomial and you evaluate it certain points of the finite field. Okay, that is how you form the code word. So I'm going to show you that construction because it's easy to grasp. And later on, of course, now nobody does it like that, but they're all done with the generator polynomial. So that's that method I will tell towards the end. So how do we construct these things? These are a special case of BCH code. So you have bit stream. Okay, you divide it into basically 8 bits. Take 8 bits together. Okay, chop it into 8 bits. You know that each of these 8 bits corresponds to a ASCII value, right? Byte. So this is your byte string basically, and then this is the integer representation. Okay, or you can split into messages, right? So this is how you do it encoding. So the thing is that first of all, these message bits, we should be able to write down the polynomials out of it. So here is the construction. So we are looking at a field with q number of elements, 16 for example, or whatever. By the way, Reed-Solomon codes are also used in QR code. QR code that you must have used QR code anytime when doing payments. So there also QR codes are, these Reed-Solomon codes are used. Wider applications anyway. So you take message bits m0, m1, m2, mk minus 1 over a field with q number of elements. K bits are there. Now we form this polynomial known as message polynomial. So let me type it here. Okay. So m0 plus m1x plus m2x square and so on up to mk minus 1 x per k minus 1 form the message polynomial. Fine. That is a possibility. Now what we do, take vector C consisting of C0, C1, CQ minus 1. So I am right now taking a vector of length Q. In the literature, you will find Reed-Solomon codes with length Q minus 1 as well. That's okay, slight variation. But this is the original paper which I am describing to you. So C is a code word in the Reed-Solomon code. So C is something like C0, C1, CQ minus 1, where each Ci is P of alpha raised per I. So it's like P0. So we are actually taking certain points. We can take n points also out of these q points. Okay, and we try to evaluate it, right? So basically it is P0, C0 is P0, C1 is P alpha, C2 is P alpha square, and finally CQ minus 1 is P of alpha raised per Q minus 1. We are evaluating this polynomial at that point, okay, and writing as a element of the code word, bit. Okay, so what is the size, what is the length of each code word? Q. There are Q bits, right, in the Reed-Solomon code. So obviously, what will be the size overall? Okay, overall size of the Reed-Solomon code is Q raised to power K. Okay, basically, all these message polynomials, each mi, you can evaluate it, So that is a general thing. Let me show you. Yeah. So these parameters, dimension turns out to be k, and length is q here. First of all, let us see what is happening here in order to obtain the parameters. P0 is M0 from the polynomial. P of alpha is M0 plus M1 alpha plus Mk minus 1 alpha raised to power K minus 1. Right? Polynomial is there. P of alpha square we can write, and so on. P of alpha raised to power Q minus 1 we can write, which is alpha raised to here K minus 1 times Q minus 1. I'm just evaluating what are these values. Okay. Now, yeah, this is here. I think there is a problem here. Anyway, how many equations are there? Q equations, right? And this is nothing but if these values are given to us, and if I ask you to find out uh, MIs, M0, M1, M2, the message bits which were used. So what we need to solve this system of equation. Okay. So out of these Q equations, I can convert it into system of equation. It will look like this, something like this. 1, 0, 0, 0, this matrix, M0, M1, M, K minus 1, P0, P alpha is for Q minus 1, right? Okay. The whole things can be written like this system of equation. Now, basically, out of those, so there were Q equations. I have taken only K equations out of Q equations. Okay. So I have written only K equations. You can see that this up to K minus 1 only, right? So here, rather than Q minus 1, we have K minus 1 into K minus 1. Okay. Out of those, there was a system of equations. Q equations were there. I have taken only K equations. And the reason is because I want to make it a square matrix kind of thing. Okay. When there is a square matrix, I can check whether this is singular or non-singular. So we can solve. I'm trying to solve the equation, right? So that's why I have taken this kind of arrangement. So out of those Q equations that are formed, okay, by taking the message polynomial, evaluating at those points, I formed Q equations. Out of those Q equations, I have taken only K equations. Okay. How many ways you can choose these equations? Q choose K, right? Any K you can take out of it, right? Now the thing is that this kind of matrix is non-singular, and this is known as Vandermonde matrix. So I'm going to show you the complete structure of this matrix so that if this is non-singular, we will be able to solve a unique solution will be there, right? So what makes it non-singular? And that comes from next slide, what is known as Vandermonde matrix. A matrix like this is a general thing. Lambda 1, lambda 2, lambda n, lambda 1 square, lambda 2 square, lambda 3 square, cube, and so on up to n by n matrix. Lambda is our element of field with q number of elements. Okay. So if you compute determinant, how will you compute determinant here? See now, first of all, suppose lambda 1 is lambda 2. That means these two columns are same and determinant will be 0. Matrix will be singular. In fact, if you take any two lambda is same, determinant will be 0, right? So it looks like the matrix will be non-singular if these lambda is are distinct, right? And you can make sure that you can actually understand this by what you do. You just subtract from first column the second column. So lambda 1 minus lambda 2 factor you can take out, right? By subtracting first two columns. Then take the next two columns. So then you get lambda 2 minus lambda 3 out, and so on. So essentially you will get an expression like lambda 1 minus lambda 2 times lambda 2 minus lambda 3 and so on. Product of differences of these lambda i's you can take out, right? And then some left over. So whatever this lambda i's are, so as soon as lambda I become lambda j for any ij, the determinant will be 0. So as long as these lambda i's are distinct, we are safe. This matrix will be non-singular, right? I'm giving you just hints, So of course you can actually try to verify. So this is the result. If lambda i's are distinct non-zero elements of GFQ, then the columns of this are linearly independent over GFQ. Vandermonde matrix, right? These columns will be linearly independent. Okay, that's a very, very important result. Okay. Uh, so I think you can try to prove it at least, or at least see that if you take field with 4 number of elements and try to see what is happening actually, right? So elements are 0, 1, alpha, alpha square, alpha cube, and so on up to alpha raised to power q minus 2. I mean q minus 1. Because okay, so those q values of GFQ you can take as lambda I and you can form this matrix. So this matrix actually, this kind of a structure is there in the previous matrix. Here, right? Non-zero, non-zero. So no, so that Vandermonde matrix result says that as long as lambda is a distinct, other than 0, 1, alpha, alpha square, any power of alpha, if you take, right, then this determinant is non-zero. No, there is no repetition in ZFQ. Where is the repetition? No, I'm not choosing Q lambdas. I'm saying that you take any lambda is a, yeah, lambda is a anything. You see, look at this. Lambda is a distinct non-zero elements of GFQ. If you take two lambda is same, suppose alpha alpha, determinant will be 0, right? You don't want to be the same thing. As long as lambda is a distinct, this matrix will be non-singular, right? So you can actually prove it. I mean, I gave you an idea. Just take the subtraction, and then the expression will come out. If you don't want to do it for the whole n, maybe at least try 3 by 3 matrix and see, right? The expression you can actually see 3 by 3 matrix or 4 by 4 matrix, right? You will observe that as long as lambda is a distinct over GFQ. GFQ has elements like 0, 1, alpha, alpha square, length, so on, right? Power of alpha, right? You just take those things, then we are done. So this result helps us here. This kind of matrix will have a will have a unique solution. This is a non-singular matrix. Using that, you can show that. Okay. So now, actually, there is some analysis in order to get the parameters. I'm leaving some things purposefully so that I can ask in the exam. Okay. So first thing, now suppose T of the code words are corrupted in this code word, right? So from Reed-Solomon code, I'm sending this vector C, right, which is C0, C1, which is P of alpha raised per I. Each bit is, right? T bits are corrupted. That means it will affect the system of equation, right? Okay. So now, basically, first of all, we need to make sure that out of Q equations, there were Q equations, right? I have chosen K equations. So there, how many ways we can choose those equations? Q choose K ways. We can choose those equations, right? And now this I am leaving as an exercise. T plus K minus 1 choose K, where T errors have occurred. T plus K minus 1 choose K of these will give you incorrect solution. Okay. So we can get correct solutions as long as this value, again, this is using majority decoding approach. Again, this is I am leaving as an exercise. We'll be able to correct as long as this value is less than this, right? So I have written Y purposefully, figure it out so that I can ask also. And this will, I mean, you can simplify this, means T turns out to be this value. I mean, 2T is less than this, and so on. So essentially, you get distance turns out to be, because T is greater than D minus 1 by 2. So distance is now N minus K plus 1. Okay. Now, there is a result. If C is a NKD code, the minimum distance cannot exceed N minus K plus 1. This result is there actually, known as singleton bound. in general, for any NKD code, which is linear code, so which is subspace, n is length, k is dimension, d is the minimum Hamming distance. Hamming distance cannot exceed n minus k plus 1. This is the result. Bound actually. Proof is simple, but I'm leaving it. Now, in this case here, you can see that d is actually equal to n minus k plus 1. So these are the codes which meet singleton bound. So that's why they are known as MDS code. MDS code, maximum distance separable code. Maximum distance separable code, okay? So I've left purposefully two things for you to check why this is true, right? Exam is near, so you know you need to have something. And then, so basically, although this construction is no longer used, I'll show you the construction which is used commonly. This is the original way how they thought about it. That's why I mentioned it, because original ideas are very, very good actually. Okay. Nowadays, what we do actually take the message polynomial, and because these are cyclic codes, Reed-Solomon code is cyclic codes, take the generator polynomial gx as cx is code word is mx times gx, where gx is summation j is equal to 1 to 2t x minus alpha raised power j. And n here is q minus 1. You see the length is here q minus 1. In the previous construction, it was q. Okay. I can modify that construction to give you a construction for a code of length q minus 1 also from that construction also. But I'm not doing any of those things. But this is the most popular result that as an engineer you should know. Okay. But what is alpha? The primitive element of the field, right? So you can do everything like this, right? Take the power. So T is what? How many errors you want to correct? And this is a very, very user-friendly thing. If I want to correct 5 errors, so I need to consider generator polynomial gx as product from so x minus alpha square, x minus alpha raised to power 4, x minus alpha raised to power 6, then x raised to power alpha, x minus alpha raised to power 8, and x minus alpha raised to power 10 up to 5. T is equal to 5, right? So I can actually construct this. Take this as a generator polynomial, and then you are done. Code is there. Of course, these days you don't have to do all these encoder, decoder, even circuits are built for Reed-Solomon code because it's very popular, right? But the idea is this, I will show you how BCH code is a general construction of BCH code, and it turns out that Reed-Solomon code is a special case of BCH code. So that is a much more powerful idea. Again, there also I will give you the original idea how they thought about it, and then normally they do with this kind of thing. I'll show you now how do we use this kind of polynomial for the construction of Reed-Solomon code. Okay, so that original idea of the construction is original. That's why I have given you, but I mean, there's no need to. Okay, here is an example. So T is equal to 2. We are suppose field with 8 number of elements. So N is 8 minus 1. Q minus 1, right? The length is Q minus 1. 7. We are taking that polynomial x cube plus x plus 1 for the construction of G of 8. These are the elements, right? 1 alpha square up to alpha raised to 6, right? Okay. And this is the polynomial representation. This is the power of alpha representation. So Gx is what? T is equal to 2 means x minus alpha square, x minus alpha cube, x minus alpha raised to 4. Right? From that formula, you evaluate it using this, that alpha cube plus alpha plus 1 is equal to 0. You evaluate the whole generator polynomial is there. From Gx, you can find the generator matrix. Remember from the cyclic codes, I gave you the idea of generator matrix from the generator polynomial. That is there. From generator polynomial, you will find the parity check matrix. Some calculations are there. I'm just telling you how it is done. X इंटरमीडिएट वैल्यू है ना polynomial के लिए x हमने लिया था field construction में we have used some x, right? Same x, right? If you want to construct a field with 8 number of elements, I need to look at a polynomial xu plus x plus 1 over z2, which has no root, right? Alpha is the root of this polynomial, which is outside z2. So if alpha is root, that means alpha q plus alpha plus 1 is equal to 0. So you see that alpha is the root of g of 8, filled with 8 number of elements. Right? So all non-zero elements are written here of this field. Okay. So you have the parity check matrix, and hence you get 7, 3, 5. I mean, once you have this, you have the whole Reed-Solomon code 735. Okay. Another example, field with 64 number of elements. Alpha is a root of the primitive polynomial. This can simplify if based on t is 3 means this power goes up to 6. Okay, and then you can simplify, get vectors. Okay. So Reed-Solomon code can be constructed over any field. If q is equal to 7, n is equal to 6, first find a primitive element in GF7. So you know that how to find primitive element. Yesterday I talked about, last time we talked about it. Right? How many, for 5 of 6, there are 2 primitive elements, right? You can just compute this, right? From primitive element, you can find primitive polynomial. Okay. And then just gx as a power of alpha. Okay. And then you compute the Reed-Solomon code. I think we have not talked about self-reciprocal polynomials and the dual of a cyclic code, but if you really want to know those things, you can look at our lectures in YouTube on coding theory, but it's really not needed much, but if you want, you can look at it. Okay. So now I think this was used in Gross model by Robert Gross. They've used Reed-Solomon code initially in the DNA storage. And they use two kind of Reed-Solomon code, inner RS coding, outer RS coding. I will not do that right now, but what I'm going to do now is the following. I think this is the last class before exam, right? So I will give you some idea about BCH code as well, because it is a related concept here. Okay. See this, I think I gave you an idea about Hamming code. How do you construct Hamming code? By the parity check matrix, right? You take the non-zero columns, okay, and form the parity check matrix, right? Hamming code can also be think of a cyclic code. So how actually this is the way. If Gx is a primitive polynomial of degree m over Gf2, primitive polynomial, जिसके root primitive elements है, right? You saw that. So then you consider Gf2x modulo Gx, the field of order 2s for m. If alpha is the root of Gx, then 0, 1, alpha, alpha square, alpha raised power 2 raised power m minus 2 are the 2 raised power m elements of the field. Each element can also be represented as a binary m tuple. You remember, I think this will give you a code of length 2 raised power m minus 1 in case of binary Hamming code. Parity check matrix is 1 alpha, alpha square up to alpha raised power 2 raised power m minus 2. You can write down the binary extension of each as a column vector. And you remember, you will get the Hamming code parity check matrix if you remember any of the lectures anyway. So if you take this parity check matrix, then code C with this parity check matrix is a Hamming code of length 2 raised power m minus 1, because this contains all distinct non-zero m tuples. Because I've just written in the form of alpha, but you can write down in the form of binary vectors. Okay. This is a compact notation. Okay. Now, Now see the beauty. Since SC transpose is equal to 0, in other way it is written like that. If C is a code word in the Hamming code, H is the petty check matrix, then SC transpose is equal to 0, right? That condition will give you what? C is nothing but C0 plus C1 alpha plus C2 alpha square plus Cn minus 1 alpha square minus 1. Right? Are you getting what I'm saying? So Cx has a root alpha. Since C of alpha is equal to 0, that means Cx is a polynomial, right? As G of alpha is 0 because alpha is the root of the Gx, alpha is a primitive element, root of a primitive polynomial. So that means Cx, the code word is multiple of Gx, right? Because this is the condition. Therefore, Cx is a cyclic code, okay? Because this is generated by Gx. So all binary Hamming codes are equivalent to cyclic codes. So now I'll show you an example. If Gx is xu plus x plus 1 in GF8, field elements are all 8 elements are given here. And as you see that this is also in terms of polynomials here. And or you can think of it in terms of powers of alpha, right? Gx is this. Just try to understand by examples. This is a primitive polynomial of G of 8. Now what I am going to do, so 0 column we are deleting. So we have get the petty check matrix H for the Hamming code. I'm just taking a small value of M, right? Now, so you can find out generator matrix also from that, because you know that from petty check matrix you can find the generator matrix. From generator matrix you can find the petty check matrix. That is okay. Okay, so this is the representation that you need to know. Now, actually, I am going to show you that. So, first of all, Hamming code can correct how many errors? One bit, one bit flip, right? And length is 2 raised power m minus 1 in case of binary, right? Length is 2 raised power m minus 1. It can correct one bit flip, right? Here, m is what? M. 2 raised power m minus 1 is 7 here. So, what is m? 3, right? 2 cube minus 1. Okay. So, now what modification should I do in this petty check matrix? Forget about G right now. I don't worry about G. What modification should I do in the petty check matrix so that I can correct two errors? That is a question Bose Chaudhary asked. Professor Chaudhary was from Calcutta who was in US and Bose was his student. So they asked this question, very simple question. Later on, people found that Hokkekam also obtained the similar result. So then that's why it is known as BCH code. What modification should I do to the petty check matrix so that I can correct two errors? So certainly we need to add some additional columns. I mean, some additional rows. Okay. And what are those rows? Okay. And that is the key idea. Let me show you. Take this example. M is equal to 4. So their length is 15. 2 raised power m minus 1. This is the petty check matrix. I can write down all 1, 2, 3. Right. 15. All the binary expansion of 15. Right. All elements. Now what we are doing. This is the element. All 15 elements are there. H is able to correct single error. I want to add more rows. Suppose I add more rows which are some functions of previous columns 1, 2, 3. Some function f. I don't know what is that function. F of 1, f of 2, f of 3, f of 15. I have to choose f of I such that I can correct two errors. See, it's a powerful technique of algebra. Initial parity check matrix can correct single error because distance is 3. I want to increase the distance because I want to correct more errors. So I have added additional rows. Okay, I don't know what are those rows. I call them some function of these columns. Okay, that function I don't know. I will try to find it out such that I can correct two errors. Only this is a very simple idea. So how to choose this Fi? First of all, you should note that field with 16 number of elements. These things, this thing should be captured inside your brain. These are the powers of alpha. This is a polynomial representation. This is the vector representation of field with 16 number of elements. An irreducible polynomial through which field is constructed is x raised to the power 4 plus x plus 1. Okay, that polynomial that is used to construct the field. This you should know now. Suppose two errors have occurred, then what will happen? We compute the syndrome. Normally, that's what I told you about the syndrome. X is sent, Y is received. Compute syndrome. Syndrome of Y is HY transpose, if you remember. So I'm just computing syndrome HY transpose. This time, it turns out to be S1, S2 because there are two portions, right? S1, S2, right? So, and suppose two errors occurred at position I and J. Position I and J. So that means syndrome will be sum of those two columns I and J at those positions. Remember. So S1 is I plus J from this equation. S1 is I plus J and S2 is some function we don't know, Fi plus Fj. The lower portion is giving us Fi plus Fj, right? F is unknown. I and J positions are known to us where the errors are, right? So now I want to solve that F. I want to find that F. How do we find that F? Now, if I try F of I is equal to I, what will happen? Suppose we repeat all the columns as it is. Whatever is written at the top, you repeat at the bottom. So what will happen? You see S1 is equal to I plus J, S2 will be I plus J. Actually, this is an inconsistent system, right? So you cannot do anything. That is it that you can avoid. Next, try F of I as I square. Can I solve? In this case, if it is I square, so F of I is I square and F of J is J square. So S1 is I plus J, S2 is I square plus J square, which is I plus J whole square, right? S2 is I square plus J square, which is I plus J whole square, right? I plus J is S1, so this is S1 square. No unique solution. Again, there is a problem. I want some sort of unique solution, F. So what kind of modification should I do to those columns? Okay. So this is not going to work. It's all, very unique, novel idea, what they are thinking. Now they said that, okay, I is not working, I square is not working. Can I try I cube? And it works actually. See, if I do this, F of I is equal to I cube. So I plus J is S1, I cube plus J cube is S2. Okay. And so I can simplify, so from this I can find out the product of Ij in terms of S1. S1, S2 is known to us because syndrome gives you S1, S2. Okay, S1, S2 is known to us. So Ij, I want to find out the position where the error occurred, right? So from this, Ij is equal to this. So now product of is known, sum is known. I can find out the polynomial for which I and J are roots. This is known as error locator polynomial. X plus I times X plus J, which is X squared plus S1X plus S2 by S1 plus S1 squared. All this simplification, right? Yes. Syndrome, because we are computing syndrome here, you see. Syndrome of Y is HY transpose, which is S1, S2. H is a parametric matrix where you can say at arbitrary place it is I, at the bottom level is F of I. Okay, and we are assuming two errors occurred. So at ith column and jth column, sum, actually you remember that property, some of those columns will be there where the error occurred, right? So it is I plus j will give you, so one will be what? This is the sum of those columns, right? So one will give you S1 is equal to I plus j and S2 is equal to Fi plus Fj. Huh? No, I'm just saying it's not two portion matrix. I'm saying two blocks are there. So this matrix I am saying, you see, look at this. I'm saying these columns I have captured like this. Okay. Next columns I want to find, which I don't know. So this is a compact notation. This is also compact notation. I'm just trying. I'm saying that, okay, some function of these values. Okay, which I don't know. It's a very beautiful way, actually, you see how they are. So actually those 1 to 15 is nothing but those binary vectors. Okay. So these bottoms will be some function of those vectors which we don't know, which we are trying to find out. Okay. So now I said, okay, suppose this is F, which we don't know, and suppose two errors have occurred. So, syndrome will be sum of those two columns, right? And syndrome values, we know S1, S2. So I can actually equate and find the equation, solve for I and J by solving those equations. It turns out that I and J can be, so once S1, S2 is known to us, I can find I and J. Because this polynomial is known to us. Once S1, S2 is known to us, because you just compute the syndrome, X is sent, Y is received, compute the syndrome, HY transpose, you get S1, S2. So S1, S2 value you can place here. So you get error locator polynomial. So you can factor this to find I and J. Okay? These are distinct places where the error occurred. This is known as error locator polynomial. So roughly, yes. Yes, sorry. Yes. The minus is same as plus, right? Z2 business is going on, right? Binary field. Okay, so in fact, this S2 by S1 is also S2 into S1 inverse. So all these things are elements of the finite field, 16 number of elements. Either you use all the form of this polynomials or powers of alpha. Normally, powers of alpha is easy to handle. Powers of alpha, because while implementing this, you just make a table and you know what to do, right? If you have to sum two vector, two powers of alpha and so on. So decoding procedure, compute the syndrome now, find the roots of the error locator polynomial, okay, and flip the bits in those error positions, right? Because we know that we have to find which positions error occurred. In the Hamming code, single error correcting Hamming code, what was the property? You compute the syndrome, it gives you the position of the column, you flip that bit, right? Here, you are getting two positions, right? So we need to find what are those positions, right? And we can do that just by flipping those places, right? Once you find I and J. So if there are no errors, S1, S2 will be 0. Those syndrome things will be 0. If there is one error position I, then S2 is something like this, one cube. And so this is the double error correcting decoding. Okay. So the most interesting case is this one. If S1 is not equal to 0 and S2 is not equal to S1 cube, solve for the roots of the error locator polynomial. There are two distinct roots I and J, correct the error at these locations. If no roots, one root or double root, do nothing as more than two errors have been detected. That case, right? And this case, more than two errors have been detected. So actually, you are able to correct only in this case, right? Two errors you are able to correct. This is a very simple idea. Take the parity check matrix, add more rows, so that you can correct two errors. And they said, why stop at two? Now add some more, right? Add another bunch of rows and ask, can I correct three errors? Okay, can I correct four errors? Or in general, can I correct T errors? Initial block of parity check matrix values of the Hamming code. Okay, and then you take some powers, beautiful construction. It turns out that BCH code are almost mother of all good codes, beautiful codes. All are a special case here. And they are very engineer friendly. You want to correct 6 errors, you know the T, and you can actually just use generator polynomial GX to construct the code. And because you see, here we are using only generator polynomial business here. So let me show you if I have that slide. So now you see in this case, that is the length 2 raised power m minus 1. I gave an example of m is equal to 4. In general, parity check matrix will be what? 1 alpha square alpha cube up to alpha raised power 2 raised power m minus 2. This is the parity check matrix of the Hamming code of length 2 raised power m minus 1. And the second block is cube of it. You see, because we found f is cube. 1 alpha cube, alpha 6 and so on, right? Now, why it is cyclic? I mean, we want to find cyclic code, right? Generator polynomial. You see, we have HC transpose equal to 0 if C is a code word, right? That's the definition. If C is a code word, or if X is a code word in C, HX transpose is equal to 0. If you remember from the parity check matrix point of view. So that means if C belongs to C, from here you will see that, so here actually C of alpha will be 0 because of that condition. Because the first portion, 1 alpha, right? 1 plus C0 plus C1 alpha, like that you can find. So finally C alpha is equal to 0. We just saw that. Similarly, second portion will give you C of alpha cube is equal to 0. Right? So, where Cx is a code word. And actually you see, this is the cube business. I think for m is equal to 4, you see this portion is, up to this portion is 1 to 15. And this is the cube business. All the columns which are open through cube. The cube means what is happening? Shifting. Right. So some power of alpha will go to some other power of alpha, right? So essentially another new representation of the things will come. So really very beautiful way, right? You construct the codes, right? So you can actually now, this reality check matrix will help you to correct 2 errors. Okay. So as I mentioned, SC transpose condition gives you C alpha is equal to 0, C alpha cube is equal to 0. Therefore, generator polynomial is M1x into M3x. These are the minimal polynomials. Minimal polynomials containing alpha as a root, right? So basically, that way, in general, the parameters are for double error correcting BCH code, length is 2 raised to power m minus 1, just like Hamming code. Here, in the Hamming code, this 2 term was not there, so it was 2 raised to power m minus 1 minus m. Now there is 2 times m, and distance is 5 now. So distance is 5, you can correct 2 errors. You can keep on extending this for different. So if you go, if you want to correct 3 error correcting, there will be 3 times m. T error correcting, there will be t times m, right? So you can keep on extending. This is the, I just gave you a very basic idea about BCH code. Normally, these are all done by the generator polynomial. So Gx is obtained, and then you Gx, you get generator matrix, weightage matrix, everything, whatever you want, right? So cyclic code have different decoding procedures as well. I just gave you some idea about all this business, right? So I think I will just show you how errors are corrected. So suppose R is the received vector like this. Syndrome is R of alpha cube, received alpha, right? It's a polynomial. R of x is a polynomial evaluated alpha. The only thing you need to know what you are doing when you are handling polynomial business, when you are handling vectors and so on. This is R of alpha. That turns out to be alpha raised to 11. R of alpha cube turns out to be alpha raised to 5. So these are the values of S1 and S2, right? So that means you get error locator polynomial by substituting S1 is equal to alpha raised to 11 and S2 is equal to alpha raised to 5. You get this underlying arithmetic is field with 16 number of elements. You factor it, roots are of this equation are alpha raised to 7 and 8. So you just flip the bit at, so that means error happened at 7 and 8 position. You flip the bit at 7 and 8 position. That is how you do the error correction. I just gave you with some example. BCH code is very nice, and I think 6, 7, 8 lectures can be done on that. But I just give you one idea how these things are working, right? How the idea is came up to them, how they do the calculations. Received vector gives you received polynomial. Received polynomials gives you S1, S2. S1, S2 gives you error locator polynomial. Error locator polynomial factorization gives you the positions where the error occurred, and you just flip those bits. Okay. And I think there are some examples which I'll leave it. These are there in the lecture folder. You can look at it, right? I think that's all. Now you see, the same thing can be continued. Some function of alpha raised to power I. So you see, a typical column in reality check matrix of Hamming code was alpha raised to power I. Some function, another function you can do as many times as you want. And again, vendor mode matrices plays a very important role because what you are doing is powers. Powers you are doing, right? So again, that kind of matrix is playing a very important role here. I think that's all. I think I showed you this, right? I will stop here. So I gave you some idea about BCH code. I wanted to cover this so that we can ask questions, right? So you have how many times? How much time? 4th September, right? Okay, so I have to prepare the paper. I guess 4 questions. I gave you sample paper yesterday night, right? So it will be fun. Hmm? Huh? For both of us. So actually, but yeah, so you should be able to do things, right? I mean, one question is obviously a bit non-trivial, which will allow you to think. Whatever we have covered is there. If you want to know more about the correcting codes, you can watch coding theory lectures where more details are given. Because this course is not about coding theory, otherwise I would have covered all those things. So some basics I have given you the idea of BCH code and reasonable code. These are important ones, right? And many others are there which we may cover as and when required, right? So I think that's all. See you in the exam.